Good morning, or depending on when you're watching this, good afternoon, good evening, or good night. I'm your Calc 1 instructor, and today we're going to be looking at the mean value theorem. Recall that our goal for this chapter is to optimize various quantities. By optimize, we mean to find absolute maximum or absolute minimum values, which we defined in the previous section. We took our first step yesterday by learning to find absolute maximum and minimum values of continuous functions defined on closed intervals, the ones that are guaranteed to exist by the extreme value theorem. In order to generalize, we want to learn how to find local maximum and minimum values. Before we can do this, however, we need to go over a couple of important and powerful mathematical theorems. The first result we will talk about is Rolle's theorem. To apply Rolle's theorem, we need a function f that satisfies these three properties. One, that f is continuous on a closed interval from a to b, that there are no gaps or breaks in f on that interval, so its graph can be drawn without lifting your pen. Two, that f is differentiable on the open interval from a to b. That is, f prime of x exists, and the graph of f is smooth, without any sharp corners or kinks. 3. That f of a equals f of b, so the function is equal at the endpoints of the interval. Now here are some examples of functions that satisfy the three hypotheses of Rolle's theorem. Verify that indeed the graphs are all unbroken, smooth, and satisfy f of a equals f of b. Now take a moment to pause the video and answer this. What else do all of these graphs have in common? If you said that they all have horizontal tangent lines, then you'd be correct. The conclusion of Rolle's theorem is that there exists at least one, possibly multiple, numbers c between a and b such that f prime of c equals 0. In graphs b and c, we see that this number is unique. There is exactly one number c with a horizontal tangent line. In graph c, there are two numbers c1 and c2 that both have horizontal tangent lines. Looking at the first graph, in graph a, every single number there has a horizontal tangent line. Note that in all of these graphs, these C's are also the location of either local maximum or local minimums, peaks of hills, or the low points in valleys. This observation is key to why Rolle's theorem is actually true. So now here is a quick sketch of the proof of Rolle's theorem. I know that none of you are math majors, but this chapter is a very good example of how mathematics is really done. We start with some basic results. In this case, will be the extreme value theorem and Fermat's theorem. And then we use them to prove new theorems, which will prove Rolle's theorem. And then you can use the new theorems to prove even more theorems, which you can use Rolle's theorems to prove the mean value theorem, although I will not be presenting that proof. As mathematicians, we do this for 40 years, and then we die. Now, obviously, Rolle's theorem is true if f of x is a constant function, since we know the derivative of any constant is 0. So let us suppose that f of x is not constant, so that not all f values are equal. Then either f of x is greater than f of a, or f of x is less than f of a for some x. So let's just consider the case where f of x is greater than f of a. Now, since f is continuous on a closed interval, the extreme value theorem says that f has absolute extrema, and in particular, an absolute maximum attained somewhere in this interval. However, we know that, again, there is at least one x value that is greater than both f of a and f of b, since f of a is equal to f of b. Therefore, this maximum cannot be attained at the endpoints of the interval. Thus, this maximum is attained at some c in the open interval from a to b. Now, what do we know about absolute maximums that are attained inside of an interval as opposed to the endpoints? Remember, by the observation we made in the last section, that this means that this absolute maximum is also going to be a local maximum. Now, what do we know about local maximums? Well, we know that they are, by Fermat's theorem, located at critical numbers. A critical number, remember, is a number c such that either f prime of c equals 0 or f prime of c does not exist. Here, however, we are assuming that f is indeed differentiable. Therefore, f prime of c does exist, so f prime of c equals 0. Thus, we conclude the proof of Rolle's theorem. Now let's consider an example where we apply Rolle's theorem. When we use Rolle's theorem, we need to verify that we are actually allowed to do so. So here, we will verify that this function, f of x equals x plus 1 over x, actually satisfies Rolle's theorem on the given interval from 1/2 to 2. And then we will find all numbers c that satisfy the conclusion of Rolle's theorem. In other words, all c such that f prime of c equals 0. So to start, is this function actually continuous on the closed interval from 1/2 to 2? Well, the answer is, yes it is. And we had a theorem way back when from chapter 2 that said that all elementary functions, that is, all polynomials, rational functions, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions, that all of these types of functions are all continuous on their domains. Here, f of x is just a rational function that is only undefined at 0, since that makes the denominator 0. Therefore, this function is continuous everywhere but 0. Good. Now, is the function differentiable on the open interval from 1/2 to 2? Remember that to be differentiable just means that the derivative, f prime of x, exists. So let's find the derivative and see what its domain is. Recall that 1 over x equals x to the negative 1, so we can use the power rule to find f prime of x equals 1 minus x to the negative 2, or we can rewrite this as 1 minus 1 over x squared. Now this, again, exists everywhere except at 0, so f is differentiable everywhere except at 0. Therefore, this function is differentiable on the open interval from 1/2 to 2. Finally, we need to verify that f of 1/2 equals f of 2. So this is just a matter of plugging 1/2 and 2 into our function f. Indeed, f of 1/2 equals 1/2 plus 2, which is the same thing as f of 2. Now, to find all numbers c that satisfy the conclusion of Rolle's theorem, we just set the derivative equal to 0 and solve for x. So we solve 0 equals 1 minus 1 over x squared, or adding 1 over x squared to both sides, we get 1 over x squared equals 1. Or multiplying both sides by x squared, we get x squared equals 1. Or taking the square root of both sides, we obtain x equals plus or minus 1. Now, this isn't necessarily our final answer. We have to look back at the interval we started with, from 1/2 to 2. Only positive 1 is in this interval, negative 1 is not. Therefore, our final answer is just c equals positive 1. Now, next, we will take a look at a generalization of Rolle's theorem called the mean value theorem. We keep the first two hypotheses of Rolle's theorem, that of continuity and differentiability, but we drop the requirement that f of a equals f of b. This gives us that there is a number c in the open interval from a to b, such that f prime of c equals f of b minus f of a over b minus a, which you might recognize as the slope between the points a, f of a and b, f of b. In other words, there is a point where the instantaneous rate of change, the derivative, is equal to the average rate of change, the slope of the secant line over this interval. I turn you once again over to Patrick JMT, who will go over this theorem as well as an example of using it. Adieu!